Okay, so now we're going to be discussing about the Bernoulli differential equation. Now, the Bernoulli differential equation, to explain it in words, is a first-order, nonlinear, non-homogeneous differential equation. So what do I mean? We have the following form: dy dx plus p of x y. This is familiar with our first-order linear differential equation, but with one exception: q of x y to the n. Now, n cannot be 0 or 1. If it was in fact 0 or 1, then we have a first order linear differential equation, and we can apply those methods. But we can't have it be 0 or 1. Also, we can't have q of x equal to 0. This is what makes a Bernoulli differential equation, a first-order, nonlinear, non-homogeneous differential equation given by the following form. So how do we go about solving this? One, we don't even solve it. Actually, rather I should say, we don't go about solving it head on. What we can try to do is try to make it into a form that is similar to this. How do we do that? Well, let's try something. We divide y to the n to both sides. Y to the negative n dy dx plus p of x y to the 1 minus n equals to q of x. Okay, suppose that we let u equal to y to the 1 minus n. If we take du dx, we get 1 minus n from the power rule. Then we keep y to the negative n. And then we have, by the chain rule, dy dx. Now, in this situation, it appears that in order to go from a nonlinear, non-homogeneous case to a linear, non-homogeneous case, which we can approach, we just have to multiply by 1 minus n. So when we do that, we get 1 minus n, y to the negative n, dy dx, plus 1 minus n, p of x, y to the 1 minus n equals to q of x. Notice, by our substitution, this is u, and this whole thing is du dx. So when we put it all together, we have du dx plus 1 minus n p of x u equal to q of x. And from there, we're able to solve using first-order linear differential equation methods. I won't bore you with the details, but the result is very similar, scarily similar, to what we've seen with first-order linear differential equation. Same exact approach. So now I will enumerate the steps in order to approach this problem. Given this form, first things first, check that it's in this form. If it isn't, make it into this form. 1. Determine or let u equal y to the 1 minus n. 2. Du dx is equal to 1 minus n y to the negative n dy dx. Multiply this to both sides. Turn it into du dx plus 1 minus n y to the 1 minus n p of x u equal to q of x with that substitution. Oh, sorry, I just realized something. I did an unequal operation here. 1 minus n q of x. So we have 1 minus n q of x. And then we solve using first order linear methods. What does that mean? We have something of the form u is equal to 1 to answer 1 plus c divided by I. 5. Now, given our substitution, we have to give it back. 1 y to the 1 minus n equals to answer 1 plus c divided by I. So using this approach, we can solve any kind of Bernoulli differential equation. And just to recap, a Bernoulli differential equation is an extremely special case of first order linear differential equation, where we have a first order nonlinear, non-homogeneous differential equation. And our goal is to turn it from a first order nonlinear, non-homogeneous to a first order linear, non-homogeneous differential equation. And as such, we're able to solve for y using the following methods. In the next video, I will give one example of how to approach the first order nonlinear, non-homogeneous case, and we're able to see that it's exactly the same as if we were just solving a first order linear differential equation. Okay, thank you.